Thanks for.
Yeah, thank you for reminding. Yeah. Right. So then basically, I think there is a very important question that can this at all be written, and can this, so you see that this is also trace of, rho F A dagger. Right. So basically, that's I think what Glauber, Sudarshan, and all these people showed. Like not all of them showed. I think Ditarka was making some very nice anecdote. He will just add. Let me just kind of say that we kind of assume that P alpha alpha star exists, and then not only rho, but you can also express any operator. In fact, right? So for example, any operator A can also be expressed in terms of some function times alpha alpha d2 alpha. So you can actually basically go into this kind of representation, some p representation, and the key point to remember is that this quantities alpha alpha star are basically actually you see is the what you were saying that this is actually the diagonal elements of this operator in this eigenstate basis. But remember that one very important property, in fact there are many properties of coherent states, we didn't even go into all that, but one very important property is that they are not orthogonal, so they form a complete basis, but because they are not orthogonal, so our usual intuition is to just imagine like think of orthogonal basis. So because they are not orthogonal, they basically form an over complete basis, right? Because they still integrate to identity. So this is, if you actually just expand this the way we did it earlier, so you see that this is basically and I'm expanding in a number state basis, so Fock state basis. So here you see that this is just this usual coefficients, and and then you have this quantities. So you see that this fact that they're over complete is kind of shows here that if you go back to where our intuitions work, which are basically this actually an orthogonal complete basis, which are the Fock state basis, the number states, there you see that there are off diagonal terms. So basically I think that is when if you keep thinking that they are not complete, like they're basically non-orthogonal, then the question is really then also there's a very important mathematical question, right? That given this non-orthogonal basis, is there a combination such that I can write it in this way? This is not a trivial question, and that's I think the main comment I had. So I think Diptarko, you want to add something?
Yeah, just
you can write on this also, no? There's a way. I think this other one had that. You can share with some other.
Can I share? Let me see.
Yeah, why don't you share it now, and then I'll get back to that.
Let's see if okay, all right. So let's see. Okay, so what I wanted to show you guys that. Yeah, so this is the paper which is usually cited, where this is the paper by E.C.G. Sudarshan from 1963. You see, where he uses this. So this is the arbitrary. So you see here below equation 2. This is the arbitrary density matrix, where psi n. This is the old notation. So psi n is the energy the number in the number basis. This is ket n. And psi dagger n prime is bra n prime. Okay, so this is a completely general density matrix.
Non-diagonal, right?
Non-diagonal with all non-diagonal components, and okay, and then here you see this equation is the completeness equation that we have written down for the coordinate state. This 1 equals to 1 over pi r dr d theta. So you just write d2 alpha in terms of r and theta. So that's r dr d theta. This is alpha. This is bra alpha. This equation actually is equivalent to equation 2. That can be, that's a way to, there's a way to show this. But then there is this. Then he directly writes down. You see. This density matrix in the diagonal form. Okay, this is directly written down in the diagonal form, and there's a citation 6. Okay, where and this is directly written down in this diagonal form. Basically, one way to understand this mathematically from this representation, equation 2, is that for each of for this n, you use you use r power n, and for this other dagger n, you use the other r power n, and the r power n you can write in terms of derivatives of an exponential, right? Because if you take n derivatives del r of e power r square, if you take n derivatives, you will get r power basically you'll get r power 2n, right? You see, you take or you actually get r power n, right? You take a derivative of e power r square with respect to r. It'll give you 2r e power r square, right? And then you take another derivative, it will give you a higher power of r and so on. So these r power each of these r power n is replaced by this derivative, and and you see here there's a psi n and a psi n prime. For the n prime, you take the derivative with respect to n prime. Okay. And then this n factorial is then decomposed into this, but then there's this heuristic way to understand this, but the proof of this, which is this citation 6 in this paper, if you look at citation 6, that is a to be published paper by Clowder. Okay, and then what John Clowder was doing was at the same point, he was developing this theory of representation of over complete set of states, and there's a series of papers. I'll just show you some. So this is continuous representation theory 1, and then the actual complete paper is this one on diagonal coordinate state representations for density matrices. This is by Clowder, McKenna, and Curry. But here he cites these series of papers. I think there's 1, 2, 3 papers. There's one, then there's also, I think there's 2. Okay, I'll come to that. Okay, there's a 2 and there's a 3 and so on. But so there's a series of papers where he shows that it is possible in some limit to express any density matrix in the diagonal basis, but the function that p alpha alpha prime, which Saikat was writing, that it's one has to show that really that will exist for some arbitrary state, and I think that is still an open area of research. I think there's this physicist from India, C.L. Mehta, brother of another very famous physicist, M.L. Mehta, who actually found out, I think this is the paper. This is the paper, yeah. Who actually found out a very nice representation of this function P alpha alpha prime, but which only works in some of the cases. So yeah, we can give the link to these papers, and maybe we can come back to this at some point again, and it's really fascinating to see how means such a simple thing, but there are still a lot of open.
There's some midterm problems, I guess.
Yeah. Okay, so I'll stop sharing.
Okay. Yeah, so let me get back to. Yeah, so one thing is that this, I think this part, just to add to that historically, this part has a name in optics, quantum optics. So actually, like, besides Sudarshan being one of the fathers, like, you know, he was a great high energy theorist also, but he being one of the fathers of quantum optics, there's another Indian guy, his name I saw, Sudarshan, was Diptaro, can you add that paper to the website?
Yeah, sure.
If you upload that, and I think Mukunda is thanked there, no?
Yeah,
and
actually, there's a paper by Mukunda also I wanted to show.
Okay, so let me just quickly write this, because this is where all this, Mukunda is also one of the fathers and leading physicist in India, presently in IISc, right? So he was, I think, a Sudarshan student, and he has played a major role throughout in not only this formulations, but later, ways of using coherent state-like things to estimate entropy and so on. Not entropy, sorry, the entanglement. So this is usually called the optical equivalence theorem for people in optics or quantum optics. So this equivalence between these two representations and existence of this P alpha alpha star. Yeah, so you can get back since today is Saturday, Litarko.
Mukunda is now in ISER 1.
Oh, I see. So this is more recent.
Yeah.
Yeah.
Okay. So your sharing has stopped. Should I share?
Yeah, if you want to show Mukunda's paper, I don't know.
Oh yeah. Let me share.
Just you can flash us because he's a
Yeah.
physicist in India, and the Indian contributions in quantum information are huge, actually.
Yeah. So I think this is the paper. Probably, let me see. No, there is a lecture note. This is N. Mukunda's paper. So this is written. This is actually like a review. This is a very nice review of this generalized coherent states and operator properties. And so it's this section especially very nice review of coherent states. And here there is another formalism. This is called the displacement formalism. These I think will show up if we talk about squeeze states and so on. So there's this displacement formalism to discuss also the coherent states. So these operators find very natural action on coherent states, these displacement operators. And here again, once again, he discusses all these properties of coherent states and this diagonal representation, which is a striking consequence of overcompleteness, is there. And then there is this formalism of Clowder, which I was showing you, which are these series of papers, which is basically let me find it. Yeah. So sorry. Continuous representation is diagonal. This is meta. Okay. So yeah. So the series of papers by John Clowder, which develops this formalism of representation using a generalized coherent state of the density matrix, this diagonal representation. Then there's this discussion of that. Of that formalism. So this paper I can keep in the
yeah, that would be very nice.
So this I can keep on in our place. And one thing which Sharikat was saying, this overcompleteness comes from this fact that they are not orthonormal, and that I think if you just calculate that you can already see if you calculate say the coherent state alpha inner product with the coherent state beta, you'll see that this is proportional to, this is almost zero. So this is proportional to e to the power, this exponentially is.
Yeah. And it depends on the distance, actually.
Yeah, it depends on the distance between alpha and beta. It's mod alpha minus beta squared. So there is some room. This tells you that there is some room to encode the non-diagonal entries. And explicitly also you can see that each of these have non-diagonal entries, like what Saikat was writing, that because there's each of these has a sum over all the number states. So there will be cross terms. So that means there will be off diagonal entries in the density matrix, in the alpha density matrix alpha. So this will have the same equation which Saikat wrote. This will have sum over n and the sum over m.
NM.
NM.
So this is exactly the point in the last class we were saying that if you see the density matrix, it has all it's not like that. That is what actually shows that it's not a classical state at all. It's a highly quantum mechanical state because there are all this like off diagonal terms.
Yeah,
Sir, here, if we see the Fock states, they form a basis which depends on a discrete parameter, like 1, 2, 3, 4, and here alpha is a continuous parameter.
Yeah.
So
yeah. So actually, right, this is the very
it's quite
next thing
it's quite natural that it will be like covering a large space, or
no, it actually turns out to be covering exactly like so. Okay, let me get back, Devitarko. I can comment on that.
Yeah, no. Yeah, it covers the same the same space, but it covers it more.
That's why overcomplete.
Yeah,
I mean,
that's why it's over complete. So also this is another faces, CL Mehta, who has also worked a lot on these operator algebras. And this paper actually I find it gives very concrete expressions for this P alpha alpha prime for different operators. So what I mean is different operators you can write in that basis, not just the density matrix operator. So let me just share my iPad. Sorry. Yeah. So basically, you see here in this paper, for example, he talks about. Okay, so this is the density matrix operator, which is some function of a dagger. But I think he also talks about some generalized operators. Okay, so here you see this diagonal representation of the operator a dagger to the power m, a to the power n. Okay, so this is some operator. This is some. So what I'm trying to say is, let me just share my screen. Okay, it would have been better if I could write on that. Share screen. Okay, can you see the screen? Different screen. Yes, can you see a different screen?
No, sir, we can only see one screen.
Okay.
Only see
Now
we can see.
You can see. Yeah. So just so using completeness, which was this equation, it's possible to write any state, right? That any state you can write in the coherent state basis, right? Where this is some this we know that alpha with any number, this with any number state, the inner product is proportional to this alpha to the power n by n factorial. So there's this e power minus alpha square, right? The inner product. So then what you can do is basically any operator you can write in this basis. Basically, you look at the operator in this number state basis, and this matrix element you can express in terms of, so naively two resolutions of identity you put. So then this is alpha or beta, and then there is alpha, there's beta, and there's alpha psi, and then sorry beta psi, and then the beta m, and then there is alpha, there's n alpha, right? So basically Here you see this is expressing any operator in this in these are all again complex. These are all just complex numbers, complex functions of alpha beta. Okay, and they also depend on m, but these are all classical things. So any operator you can find a representation in this in the coherent state basis. And this paper by Mehta, he actually finds what is the representation of the operator a dagger to the power m, a to the power n, this operator in the coherent state basis. And I'll just show again the answer. So yeah. So here you see this. This is the representation. So there's this phi v. So basically any operator. Let me just see his notation. Yeah, you see any operator. So this phi v is what we were calling p alpha alpha star, and this is for the density matrix. But you can talk about the representation of any operator, and the representation of the operator a dagger m a n turns out to be this. Okay, so it is possible. So here this operator is very explicit because you see clearly this destroys from the n. It destroys n numbers from a state, and it puts back m numbers in the state. So it connects off diagonal elements. So, but there is still a diagonal representation of this operator in the coherent state. So yeah.
Yeah.
Hello,
Yes.
sir.
Yes.
Sir, probably I lost the logical. So I'm going back to primary question. I want to understand the meaning of alpha. I mean, alpha, the eigenvalue. So
Yeah.
what exactly it will tell us about the system? I mean, for number state, if then n is the number. I mean, n is the number
Yeah.
of photon or phonons. So what
Right.
is alpha?
You mean if you can measure?
Yeah, so this is not a Hermitian operator, right? So I don't know. We can't measure alpha.
Yeah. So
So, but you can, yeah.
you can
You can basically express A as sum of two Hermitian operators, like with an I.
x plus ip.
So it's a normal operator, and there's a general theorem we can show that any normal operator can be expressed as H1 plus some IH2, right? And H1 and H2 you can measure. And what that really means is actually literally measuring alpha is measuring amplitude and phase of an field, basically, electromagnetic field. So that's actually what is the plan in the class today, to do some of this interferometry eventually.
Okay,
So you'll see that both of these things you can measure very well. And even for things like any arbitrary state. Yeah, so should I go get back?
Yeah.
Yeah, and maybe there were a few other things, but since this question came up, this is something.
Sir,
which,
but those two operators doesn't commute like x and p.
huh?
Like
That is
x and p, they doesn't commute.
Yeah, so these are separate measurements you'll have to do. So if you just hold on a little bit, this is exactly all these issues that, like you remember, like we talked a little bit, we'll talk a lot today on this kind of rotating the basis, and then what looks like sigma z you're measuring, but then you can rotate, and then sigma x are just probabilities basically you measure in that rotated basis. So you keep rotating your basis and take measurements to see these things. And this is kind of the idea, like I have kind of used once this word tomography, state tomography. If you see that the word tomography normally we hear in terms of brain scan, brain tomography, and so on, where you have a complex 3D object and you really cannot take its image. So you basically do this tomograms, right? You take like its shadows in different planes, and from there you try to reconstruct. So the equivalent thing in quantum measurements are basically changing basis and looking at different things, basically. So non-commuting operators you're measuring by changing basis. So yeah, any other questions regarding up to this point? Since we are at it, and there was a similar question right now, so let me just also a quick, very basic note, like this quantum one, maybe first week of quantum one, that, you know, like if you actually see that we are talking of the states also, for example, even for harmonic oscillators, like states like Q and P, which are like, you know, states of operators Q and the position and momentum. And if you actually see, this is just as a note, you know, so that we remember, particularly we will be talking a lot of measurements in this basis. These are continuous set of values Q and P. But if you actually see, one very interesting thing about these operators are that these operators are technically not normalizable. You know, in the sense that, or the states are not normalizable, in the sense that, you know, you do not really have Q is 1, you know, but actually what you do have in the integral sense is identity, you know. So actually, if you see, this kind of implies that you have kind of for QQ, actually it's not 1, but it actually kind of diverges. Right, and just from this kind of a continuous representation to this is very nice. I can just pull this up. So basically, you see that on this state, when we actually project in this state, we get this function which we call the wave function. So this is a function in the Q space, you know, but nevertheless it's projected in this you know, this kind of strange, what happened to this strange bases which are not normalizable. And if you see, you can reconstruct your actual state if you know these things, right? Like if you know psi q, you can actually reconstruct your state. So so basically this is something technical, maybe Diptarko again can add a little more, but you see that there is a like, similarly we are talking of this existence of this kind of functions, you know, this classical functions corresponding to these systems, and you see that there is a constraint on psi q, which is basically its norm, or what they call the LQ, the L2 norm actually needs to be finite, or rather, you know, it should be normalizable. So this apparently, you know, the the mathematicians can go on and on this, but this basically says that actually the you know, the space of Q is countable, in the sense that, you know, like if I just very kind of draw diagrammatically, so the values corresponding to Q, though, you know, they're infinite, they're countably infinite, and that is kind of the correspondence between the corresponding states we, you know, the integer numbers we put for the states n, you know, corresponding to the harmonic oscillator state, that it's countably infinite, you know, but Q is actually eventually a limit of a continuum, like, you know, it's a continuous variable, and the corresponding Q, so technically they are not really in the same Hilbert space, you know, but you can actually label them with integers because of the fact that they are not normalizable. And as a result, you know, when we are writing, this was a question I think asked long back, and I'm just getting back to that. You remember that when we are writing this kind of continuous variable, you know, POVMs, we are putting these DQs, which were kind of like keeping this, you know, I should not use the word discrete, but this kind of like brainy, like labeling option, like, you know, of this kind of continuous variable representation. Yeah, Diptarko, you want to add anything to this? Or?
Yeah, so yeah, I means many of these steps actually involve exchanging summations and integrals. So if you express the coherent state, because it involves an infinite summation, and many of the times you have to either move that summation inside an integral, or you have to move an integral inside a summation, and those manipulations you can do only when the summation is convergent or the integral is convergent. But basically, if they have a finite radius of convergence. So, and this is an assumption which physicists make often, that that's why it is difficult to actually prove that such functions will always exist. So, so this is one thing, and even in this simple expression, which actually this Sudarshan paper uses to write the completeness. So the completeness equation is this integral over d alpha and d alpha bar, right? And you have the ket alpha and bra alpha that's equal to 1. And then you can exchange the integral into, you can write the integral in terms of r integral and a theta integral. But then there's a way to write that completeness just in terms of a theta integral. And on the right hand side, instead of 1, you have sum over discrete states. So if you try to derive that, so that may be a homework for you, that if you try to derive that, you will have to bring the summation. You have to take the summation out. You have to bring the summation inside the integral. So, and that you will immediately.
You can write a little, I think, maybe.
Yeah, maybe I can write.
I think it might get just vague too.
Yeah, okay. Then maybe.
But these are very basic, like quantum one things we are talking of. But this, even when we are doing harmonic oscillators, what we mean by the Q and P states as opposed to the N state. And how this
I just wanted to show the subtlety that's there. So basically, we all know this relation, right, of the completeness, that 1 by pi r dr d theta r e power I theta r e power I theta. This is 1. Okay, and now this is also equal to sum over n nn. If I write in this is the number basis. Now the equation which Sudarshan uses, once again without any proof, is this equation. This is equal to e power minus r square, n going from 0 to infinity. This is also 0 to infinity, of r power 2n by n factorial n. Now, how will you prove this equation starting from here? So there's a trick that you use the gamma function. So you know that gamma of n plus 1, if n is an integer, this is n factorial, and that's equal to, if you just write dt 0 to infinity t power n e power minus t. Right? That's just gamma function. Therefore, you can write, or let it be some other number, integer m. So then you can write m. You can write 1 as 1 over m factorial dt t power m e power minus t 0 to infinity. Okay, and now let t be equal to r square. Okay, so then this is 1 over m factorial. So then 1 is 1 over m factorial 0 to infinity drr. Actually, there's a factor of 2 also. So there's a 2. 2 is not important here. Okay, 2. Actually, yeah, 2. And then there's r power 2m. R power 2m e power minus r square. Right? Yeah. So then you see that this is the number 1, and this number 1, this equation for number 1, you plug it here. Okay, this is just number 1 that you are inserting. So you have, so here from this equation you have 1 over pi drr d theta. Oh, that 2 is important actually. Okay, so r e power I theta r e power I theta, this is equals to n, and then you inserted this 1, and this is true for any integer, right? So express this equation in terms of n, in terms of the same integer which you are summing. So this is true. This is equal to 1 for any value of this m, any integer. Okay. So this is important, that this is for any m. This is the property just that the gamma function calculates the factorial for you. So then this you express it in terms of the same integer. So this is 2n factorial 0 to infinity dr r power 2n e power minus r square n. Okay. So now you see that you're basically done. If you want to prove this, all that you need to do is to get this outside this summation. Okay, then you can take this part common on both sides, and then you have this equality. So, but then what you have to do, you have to exchange this summation with this integral, and that you can only do if you know that this summation converges. Okay, so you have, so now you have basically this equation 2. Let's bring the 2 on the other side, so it starts looking more and more like what we want to show. So you have drr 0 to infinity, and you have 1 over 2 pi d theta r e power I theta r e power I theta minus, you have this okay, minus I'll write later, this and then you have this equals to n equals to 0 to infinity 2 over n factorial. 2 over n factorial also will bring outside. So this is drr again 0 to infinity r power 2n over n factorial e power minus r square n. Now basically is the step that you change this, bring it outside this summation. And if you do that, then you have this identity. Okay, and then this is the identity which then once you have this identity, then there's this other manipulation where you want to write an identity with not diagonal, but you want to write an identity for non-diagonal n prime. So what you do is, instead of 2n, you replace it with n plus n prime. You replace this factorial with this factorial with basically n plus n prime factorial divided by square root n factorial n prime factorial. Do this replacement. When n equals to n prime, it goes to this. So you do some replacement. So this part I'm not sure, because it directly writes down the answer, citing this Clowder's formalism. So, but you see these manipulations are there, and then I think more rigorous people like Clowder has to work hard to show that these will hold in most cases. Okay, so it's the same thing with plane waves, where these are not they are not normalizable states. So in some sense, these are not physical states, the e power IPX kind of states. So maybe Shoykot will start talking more about these kind of ambiguities that we live with. Okay, so this is not a homework now.
Yes, so any questions?
Hello, sir.
Yeah.
Yeah. So the expression that we just saw, that was starred there, that we are trying to prove in the previous note.
Oh, sorry. Yeah.
Yeah.
Yeah. But
So we should have. You want to go back? Okay. Yes.
I can ask. Yeah, I can share. Sorry. Yeah. Tell me, Anurag.
Yeah. So I was asking, like, do we really have to do this roundabout way about proving this? Because from that expression, if we just replace the r e to the power I theta states with a Fock state representation, then do the theta integral, the theta integral will give a delta n minus n prime, and that will just collapse into that form that we have written.
Yeah, but do you don't have to use any. Yeah, so maybe it is possible, but here I wanted to show that
You are not
have
sharing,
to,
Diptarko.
Oh, okay. Sorry. I'm not sharing. Share screen. Oh, sorry. But anyway, maybe now it is sharing. Okay. Yeah, what I wanted to say is just that I wanted to point out just that you have to exchange. So this is a special case, but this exchanging these two objects, right? So maybe here you can get by explicitly using the number state representation of the coherent state, but in many of these manipulations, to prove the existence, you have to do these kinds of manipulations.
This is an exchange in the continuous to the discrete.
Yeah, there's
sum
an
of interior
exchange
relations.
of, and then these kind of exchanges one can only do if things converge.
One can you repeat that? Your
Yeah,
voice.
one can only do this kind of exchanges when things converge, when the summation has a finite radius of
Yeah,
convergence.
so the norm is conserved.
Yeah.
So the L2 norm is conserved.
L2 norm is convergent.
So that is a presumption we make when we assume that we're working in a Hilbert space, right? Our norm will always be finite in that case. So we can
Yes.
always assume that.
Yeah.
Yeah.
But you sometimes one may be interested to work on say LP spaces also. So for example, so later also we'll see this thing. So we may be interested in calculating. So basically, if you look at a P norm, this is basically you calculate the pth power trace, and then you take the 1 by p root. So that means there's a measure which is trace distance between trace distance of density matrices. This we'll see later when we talk about thermalization and so on, where we try to calculate the square trace distance is just trace of row 1 and row 2. You take difference of these two matrices, square it, and take the trace. Okay, so that's a distance between these two. But you may be interested in actually calculating the distance of some higher powers of this, say row p minus row 2p, and then you take a 1 by p. Here you take a square root of this. So these kind of distances people talk about in quantum information theory, where and then to define these you need convergence of the p norm of operators.
That is the LP norm above. You can just
Yeah. This is the finiteness of this is the LP norm generalization. But you are right that the states in the Hilbert space, they are L2 normalized. Okay, because we define an inner product with just two operators. So we always have the inner product always involves basically multiplying two of these objects.
Okay, yeah. Any other question before I start sharing? No, fine. Yeah, Saturdays are better for asking questions. We can make the whole thing a tutorial.
Yeah.
So, let me make one more comment. I think following one of the questions just now or notes, that remember that this alphas or this R's we are talking of. So you see that suppose I have a single mode electric field, as I was writing before. So some amplitude square the thing times, A I kz minus omega t plus A dagger or whatever Hermitian conjugate, So if I am given a problem that, you know, consider, so this is the physical picture, that consider an electromagnetic field in the coherent state, you know. So the field is in a coherent state alpha, which is basically can be written as r e to the power I theta. So you see that if that is what is going on in your universe, then from there on, you know, E just becomes, E average is just, you see that this is just E naught, you know, R, you know, e to the power I theta plus kz minus omega t plus, you know, just complex conjugate, not Hermitian conjugate anymore. This exactly looks like a classical electric field. This is the correspondence of the why coherent states are called classical states, not because of the fact that they are density matrix. You remember, like for the density matrix, we talked about this, that another way of looking at density matrix, since I think many of you are seeing it for the first time. So we don't think of anymore of quantum states as only pure states, but this is the most general way we are writing the density matrix, where actually the diagonal terms are basically probabilities. You know, and this is the classical world. Actually, when we really mean classical versus quantum, this is what we mean, whereas the off diagonal terms are quantum. So another way of thinking about density matrix is that, as opposed to a quantum state which just talks about amplitudes and summation, like a state like this, a density matrix actually kind of starts to separate what is there in the quantum state in terms of like classical and quantum parts. You will see that we'll come to this later in a much bigger way, in the sense that when we'll talk about this bipartite systems and entangled states, which we already talked about, you know, a larger system which can be in a pure state, but you know, if you trace it over a smaller system, can be in a mixed state. But you will see that when we'll come to this is a question, you know, we have not even started talking about quantum information, except that we said that, you know, this coefficients of the wave functions are the where the information lies. But this becomes a very important question in quantum information, that given a quantum state, a density matrix, you know, what is classical, what is quantum, you know, like in that. In particular, you know, if you have a bipartite system, you see that it's very strange. It seems like when you trace over, the individual system starts picking up like this mixed behavior. It starts with, they become mixed state. And this is a question actually Wouters kind of separated out. He basically showed that effectively this states you can separate out into an entanglement part, which is purely entangling, and the rest is all classical, you know. And this was kind of the main notion behind the ideas of quantum teleportation, like very kind of science sci-fi like ideas of teleporting a quantum state, which we'll do in this course later. And this was kind of like, you know, this is kind of a very squinting your eyes, looking from far. This is one way of looking at the density matrix, that you are looking at a very general quantum state whose classical parts and quantum parts are kind of separating out. The classical parts are the diagonal terms, which are the probabilities. And the off diagonal terms are purely this quantum coherence. And given that, you see that this, but when we say coherent states are classical, we mean something very different. We mean that given a coherent state, you can basically start thinking of your classical electrodynamics and classical optics. So you see that now that you have an electric field, you see that R's are just real, like, you know, they're just amplitudes, you know, E naught times R. You know, so for example, you can do a very simple intensity measurement, you know. So E naught R square is actually proportional to the intensity. So you can just put a, you know, photo detector somewhere here and just measure the intensity. And if you say that I'm also interested in measuring theta, then you can do many things. For example, you know, if this is the electric field, you basically kind of take with another electromagnetic field, you know, so R e to the power I theta, you some known phase with which you can actually add this to, so interfere, you know, take the square of that. So you will see that, and again, you are measuring the intensity. So this kind of, again, a classical way of changing bases, and you will find that the intensity is actually proportional to this phase. So from that, this is what we call interference fringe. So from that, you can measure the phase. So again and again, you know, like this is what I'm trying to say, that this is a very important point, that you might not directly in a single measurement might not be able to measure a non-Hermitian operator, but it can always be broken down into Hermitian parts, which you can actually measure independently. You can measure R and you can measure theta, and from there you can reconstruct. So coherent state, this is what is classical in coherent state. It's not a classical state at all. If you write its density matrix, we are saying this over and over again. It has off-diagonal terms in the number state basis, but it's classical in the sense that its electrodynamics becomes that of classical electrodynamics. It becomes basically optics when things are in coherent state. And remember, at the cost of the fact that you just cannot say which, how many, what is the number of photons there, because you have constructed the coherent state by summing over, summing over all number states. So you have lost that specific number state information at the cost that you now have a definite phase.
Sir, so by making multiple measurements, the uncertainty condition can be narrowed down. I mean, that's. So by making multiple measurements, so here what we are seeing, the uncertainty condition can be narrowed down, kind of thing.
Just 1 second, I kind of lost my screen. Yeah, the uncertainty. Yeah, that is a well. What happened to this?
I think yeah, somehow in between the call had dropped.
Huh?
The call, my screen also went blank.
No, but I have somehow I moved out of this. What is the software I was using?
OneNote.
OneNote. Not. Okay. Okay. Is it okay? Yeah. Okay. I'm back. Yeah. So you are asking that using repeated measurements, so of course you can do that. This is something, I think this is going a little ahead. We'll come back to these questions. So this is really, the question is regarding the fact that I am estimating some parameter theta. So I measure its amplitude, I measure its expectation value, but then I say that what is the kind of spread in the expectation value. So that's then I'll measure some some deviation of that. So this kind of gives me some operator, like some measurement corresponding to its value. So for example, suppose I'm measuring the phase of this electromagnetic field, and here one needs to be careful about what you mean by repeated measurements. So it turns out that if you take a measurement once, actually this quantity also goes for coherent state. You can calculate these things. This is actually really the plan. We'll do these things. But actually, there's also a classical result which tells you that, if you keep repeating the measurement, your error scales as 1 over square root of n. This probably you have done in your experimental physics course or any StatMech course, law of large numbers. So that still holds for coherent states. But when you're saying repeating by repeating single photons, see, that concept is not there because you have already kind of created a state which has a superposition of all sorts of photons. So a single shot measurement of that is as if you're using many photons, and that scales basically as what is known as the standard quantum limit. So we'll come to that. I don't know if this answers this. Like this repeated measurements and so on, we have not really done yet. We'll come to this later. Yeah, but the coherent state already, in terms, if you are really thinking in terms of repeating number of photons, it already has that thing. Okay, so let me get back to where we are doing. Let us cover a little bit. What is the time? Oh, I see.
Time is 12:05.
So it's yeah. So another half an hour, or
yeah.
So dynamics is what we are doing, and the dynamics of Fock states. If we know Fock states, we know superpositions of Fock states, so we know coherent states and other thermal states and so on. So we'll basically remember, like last time we were saying that any kind of single qubit operations are just rotations on the surface of a 3D sphere. This So basically any operation is just kind of rotations, and these rotations, doesn't necessarily need to be this Hadamard and phase gates, but these are something that are widely used. So I'll start, skipping a longer story. We have already talked about many things. So let me just start with the quantum mechanics of something very, very simple and straightforward. This turns out to be a very foundational quantum gate, but in real life, in your classical life, this basically just looks like a single half-silvered mirror, so a glass basically, and you have done it such that if there's a field that comes here, goes this way, a part is transmitted, a part is reflected, and similarly one that is coming in, from this side. So this actually you can show. I'll cut that part also. So for example, there is a reflection coefficient. Classically, let me label this thing. So if for example, if an electric field comes here with amplitude E1, a part goes to E2, a part goes through E3. So you can write this kind of relations that E2 is R E1, E3 is T E1, where R and T are just reflection coefficients and transmission coefficients. This is how classically we'll go about reflection, and this is transmission. So this is just again Griffiths, if you see classical electromagnetism, so basically if there are no losses, then R squared plus T squared, the intensity of the reflected light and transmitted light should add up to 1. So quantum mechanically, when you do that, you see that the electric field becomes operator. So you need to know that if there is an operator A1, if there's an, and suppose I'll just label this also, this actually becomes very critical, otherwise you cannot have unitary transformations. So suppose these two operators are labeled A1 and A0, instead of E1 and E0, what are the relations between these operators and the operators outside? On the other side, the output operators A2 and A3. Right, and this is something you can actually write this down. So I'm just writing it. Just looking at these quantities, that A2 actually is going to be a part of reflection coefficient times A1 plus transmission coefficient times A0. If you see this two, A2 is composed of reflection and transmission, and similarly A3 is can be written as a transmitted component times A1 plus a reflected component times A0, and this R and T. So what I'm writing here is partially phenomenological, as in this is a strange semi-classical thing where I'm taking the atoms of the glass plate to be a classical quantity. So this reflection and transmission coefficients are exactly the, RT are exactly from Snell's law. If you know the material, you can go and calculate. So we are basically taking that classical. They're not, the beam splitter is classical. But you see that the electric field is quantum, and as a result, they just transform here as an operator, R, T, T, R, A0, A1. So you see that this is basically like a matrix. And this is what is happening. This is the way to, this is actually a dynamics, except that you see that the two modes are coming in and mixing, and two modes on the other side are there. So this is as if like transforming these two modes A0 and A1, which were actually literally like two directions, to the beam splitter modes after that. Any questions up to this point, this formulation? What is phenomenological? What is, how we are doing this? And if you know this transformation, you see, always remember that the electric field is actually now partially, some just complex numbers and amplitudes, but part of it is operators. You remember that these operators, if, for example, if I actually, write in the in some space, these are matrices basically, so these are one but off diagonal terms. So basically for the transformations, we need to know how the matrices are transforming. The remaining part of the electric field remains. functions.
Sir, why are there no terms that have a dagger? Because
No, exactly,
contains an a dagger term, right?
exactly. That is exactly what I was writing. So similarly, you can just write for daggers, no? So star, star. You remember that these are actually like these quantities. If you remember from Griffiths, these
Yeah.
are actually complex numbers. These things have
Yes.
like amplitudes and phases, right? Remember, like after reflection, for example, if you have a glass plate, if you reflect, the reflected light has a phase difference corresponding to the transmitted light, right?
Yes, sir.
Remember that? Yeah, pi by
Yes, sir,
2
optics.
phase shift if you are at 45 degrees. Just please look at Griffiths, this thing. So as far as the reflection and the transmission coefficients are concerned, it's exactly that, basically. And similarly, you can just write it in terms of daggers also. You see that once you know this transformation, you know that transformation, basically. Right. So, so you see that once you have this, what you really demand, like this matrix to be unitary, what actually it means is that, to start with, you had the commutation of A0 and A1, initially. This is the most sacred condition that the operators needs to satisfy. This is where the second quantization is coming from. So after also, before and after, or initially and finally, A2 needs to satisfy the commutations. Similarly, A3, and now you see that A2 is now, you can try to find the commutation of A2. It's a combination of linear combination of A1 and A0, and similarly A2 and A3 cannot commute, or they do commute, so and so on. So this all needs to satisfy. If you place that in, it's a very, very simple exercise. Just use this to place this here, and you start getting conditions on your this classical glass plate, and these conditions are again one thing that we know very well, exactly what I wrote before that, just from this A2 dagger and A3 dagger commutation, you can see that you get this conservation condition that the reflection coefficient, whatever the usually in Griffiths they write small r for the amplitudes, large capital R for the reflectivities, and transmittivities should add up to 1. But you also get another very nice thing, from this kind of cross term conditions, that you basically start getting conditions which actually tells you that R star T, just plug that in, it's really, really straightforward, should equal to 0. Which actually means that you see there are some conditions on the phases. In fact, like, you can write this thing as mod of R, mod of T times, some e to the power I phase picked up during reflection or transmission plus, the complex conjugate of that is equal to 0. So you see that the angle which between reflected and transmission coefficient is 0, which basically implies that there's a pi by 2 phase difference between reflection and transmission. In fact, one could have been more careful. In fact, more generally, if you actually go through again the Snell's law reflection from a glass plate, you see that ideally, reflection from this side and reflection from this side, if this reflection coefficient is R1 star, this reflection coefficient 1 should keep R2 star. I have taken R from two sides of the glass plate to be the same. So if you actually do something like that, you basically find that summation over all these phases, basically should add up to pi, like from exactly the same condition. So there you get basically R1T, you get all sorts of conditions. So this is actually something, again, like one very quick, beautiful thing in quantum mechanics. You see that this phase conditions, the fact that small r and small t are amplitudes, so they have phases, and how these phases should add up to this kind of a condition we don't even get for, if you go back again to Griffiths, Snell's law derivation, you don't get that. You get that from much more involved thing. You see, quantum mechanics already kind of forces you to, from unitarity, to have this kind of phase relations, So once you know that, and if you know now the amplitudes, you can start writing down this matrices. So any questions up to this point? Otherwise, I'll go ahead with how it looks like. So for example, let me just take this. Consider what is famously called 50-50 bin splitter. So you see that 50-50 bin splitter means that the reflection coefficient and the transmission coefficients are basically square root of half, R, capital R plus capital T. Either, half of the light is gone this way or that way. So this is basically 1/² square root. Right. And if I choose this difference to be pi/2, you see that this matrix actually starts looking like, some gate will come to that, but it basically looks like I1, A0, A1. You see, so it actually, this is very kind of interesting that it actually looks like some large operator. So if I say these are the output modes, this is the input modes. So it actually looks like some large operator times A0, A1. So this you can just remember that normally when we are talking of this operator evolutions, so Heisenberg representation. So it's all about the unitary T, so basically any operator is actually going as U dagger. O, I should not use the same, I think, O for, so sorry. Let me just use this. So any operator is actually going as some unitary times A. So this is F final, this is initial. This is how, remember that we reviewed this. This is how the operator evolution is going. Here, actually, if you see, after doing this kind of phenomenology, what we have written is that this operator A, like this 2-port operator, actually goes as some O times A initial. So one immediate question is that, can we actually write this O in terms of U? And here, just a side statement will come back to this, that often in this kind of dynamics, we often prefer to write things like this. You will see with the beam splitter case also, sometimes things are just easier to calculate. And this kind of a representation, we talked about is unitary transformation. When we write it in this way, these are usually called, super operators. We'll come back to properties of super operators. There's a little homework problem also on super operators, But the question is that, we now know this transformation. Can we make this change? And again, this is, I'll leave this as, use Baker-Hausdorff. Again, the same identity. So I think I've already written it to show that you can actually write, one can write this, as A0, or let me call it, I'm calling it A2, A3. A2, A3, the two output annihilation operators. And similarly, you can take the dagger to get the creation operators. These are output, can actually be written as some U, A0, A1, where U, if you use the Baker-Hausdorff, you can show it actually, I find it showing the other way easier. So U actually looks like exponential I by 4, A0 dagger, A1 plus A0, A1 dagger. Right, so this is a homework problem. There's something, just repeated use of, again, the same thing. As I'm saying, that everything that we are doing till now is just again and again using this identity, that e to the power some minus zeta A, B, A is basically, B plus this commutation of A and B and so on. And so you can beforehand calculate the commutators and then express this. So this is actually, you see, what we have kind of written down is an elementary gate operation where actually the sets of operators A0 and A1 gets transformed into A2 and A3. Why this is a gate, what kind of a gate it is, what this transformation means, we'll come to all that. But any questions up to this point?
Sir, here we've taken a elementary model of a beam splitter where you only have R and T. If you add another level of complexity and say that our a beam splitter has some absorption coefficient as well, then unitarity still be conserved there.
Yeah. So then what happens?
Then some of the electric field gets lost into the splitter.
So this is so you are asking then what happens, right?
Yes, sir.
So one thing is that like one thing that immediately happens is basically the unitarity breaks down. So actually, this kind of like unitarity, like the dynamics needs to be unitarity is same as saying that the commutation relations needs to be preserved. So these things all hell break down, but so basically something else is happening. How do you do quantum mechanics there? So that's kind of really the aim which will be starting, in the next week. So what you're saying is that there's a beam splitter, so now I'll do just diagrammatically, I'll put your question. So there's a beam splitter, but the beam splitter now has something else, which is your loss. Somewhere the photons are escaping. So what happens to this transformation, you see? So basically it turns out that, again, if I think of this operator, I need to trace out those lost things, and this exactly turns out to be the question you're asking. It's very good that you're asking that when you're whenever you're asking losses, not only beam splitters or for anywhere, even in atoms, these are basically precisely the question of open quantum systems, where actually it's very important to understand first what the question you're asking. Will come to the answer next week. But basically the question you're asking is, now there's a beam splitter, but now some intensity is getting lost, right? Like if you like, it's the same as saying R squared plus T squared is not equal to 1. It's something extra. So that extra in quantum mechanics, it doesn't give you any room. You will have to really think of also that as a quantum system, and then you'll have to look at the whole evolution of that. In fact, for the beam splitter, if everything goes fine towards the end of next week, we'll actually do exactly this thing. What happens when there are losses? And you will basically find that not only that photons will get lost sometimes, but there are also strange kind of fluctuations that gets added. Like, this is one of the main things we'll learn. And again, this is the question, same question in different ways, that there are two systems, A and B. I don't know A, I only observe A, I don't know B. How to think of A? So I combine them, but then eventually trace out B. And that's exactly the same question of losses. And you will see that the loss do not come alone. It comes with loss and fluctuations, so it makes the system jittery also. Yeah. But if I go back, any other question? I'll maybe, like there's a lot. In fact, today again, like we didn't really get a start, and yeah. So let me just kind of point out here, and maybe we'll have another extra class or just tutorial on this. But if you actually look at this thing, so what is it that we have done, right? So we basically have taken two modes. Suddenly what is happening? So two modes, A0 and A1, and we have seen how these things transform to A2 and A3, right? And this transformation matrix, we actually wrote in terms of an unitary, or rather you will have to work it out using Becker-Hausdorff. But if you look at this unitary operation, it is like, I'm calling it dynamics, but I should not be calling it dynamics, because in physics, when we are calling of dynamics, we are actually thinking of an unitary operator as if as like I, H, some Hermitian times time, or rather this whole operator needs to be Hermitian, but this is when we think of time, here we are really not thinking of time, but we are thinking of dynamics in a configuration sense, that two modes come in, two modes get out. So mixer, so really little gate where two modes are mixed. So if you look at this thing, I don't know, like if you guys have already done that in quantum mechanics generators of rotation, you see that this pi/4 looks like an angle, right? And this, as a result, like there's a tendency of looking at this, if you again squint your eyes a little bit, this kind of looks like some I times some theta times some, some rotation matrix. And if you take that, this is the same connection. I'll just write it for now. So it turns out it's exactly like a rotation. So if you actually just take this and get comfortable, very comfortable with, this squinting your eyes and doing this algebras, so this is for Schwingers, so that you can actually define these operators now. You can actually start getting more sophisticated. So this is basically A0 dagger A1 plus A0 A1 dagger, but you can also define a JY, which is half sorry, this is I have a minus A0 A1 dagger and JY JZ, which is A0 dagger A0. So this actually, this is, I think, your quantum one again when you're doing angular momentum and rotations. So these are basically exactly the generators of a rotation group. If you remember, or maybe I should not mention this now with the qubit connection is similar, but you see that these are basically exactly, you can go to this kind of this effectively a real space rotation, and Jx, Jy, Jz actually turns out to be exactly generators of rotation group. You can actually define an operator, Jx squared. I think you already did this when you did your quantum one. So this you can write as some J plus one, and this J is basically this operator J. This is actually the number operator. And I'll just come to this, what this number operators are. So this is just A0 dagger, A0 plus A1 dagger. So, we are like moving, I think this might be a sudden jump to you that, what are we talking about? What are we mixing? So all we are trying to say is that we talked about this kind of thing, the two modes, two states, they are basically transformations. You remember transformations on a space. So basically this, the fact that a beam splitter is actually taking these two states and mixing them into A2 and A3, I should also be able to visualize this thing exactly like a rotation. And indeed, these are exactly like rotations. In fact, you see that, this beam splitter here, basically now, I was being tentative here, but this basically looks like e to the power I, a rotation by an angle pi by, what happened? Pi by 2 times Jx. You see, so a beam splitter that we just now talked about, that is basically just like a rotation. So let me just write this here, that this whole thing now you can visualize. This is the last thing. For example, this A1, A2 connected, so this A1, A2 or A2, A3, these outputs were connected due to this super operators. So, if I write these operators just as, again, just bear with me why I'm using this sine alpha over 2 minus I sine alpha over 2 cosine alpha over 2 times A1, A2. In, this is for R cosine, sorry, this is R cosine alpha over 2, and T is basically, there's a I sine alpha over 2. So you see that this is a little more general. It is not 50-50. The 50-50 case will be when alpha is pi by 2, half beam splitter. So this actually you can exactly show that this you can write in terms of precisely the operators Jx, Jy, Jz, constructed with this outputs, is actually exactly looks like 1, 0, 0, 0, 0. Cosine alpha minus sine alpha cosine alpha times jx, jy, jz. These operators are basically transforming exactly like a rotation, and this is a rotation about the x-axis. So this is one point, so you see that suddenly these pictures are mixing. Very, very simple thing we are doing, that you take this beam splitter, the reflection transmission coefficients are, basically 50-50, and this exactly looks like a rotation. Similarly, maybe I should stop here, or should I just finish this little part actually? If you, for example, take take this coefficients, such that their cosine, some alpha over 2 minus sine alpha over 2 sine alpha over 2 cosine alpha over 2. If your coefficients between A0, A1 in are of this form, this is A2, A3 out, you see that they are almost exactly the same as earlier, except that this reflection and transmission coefficient here, instead of a phase of pi by 2, I have taken a phase of pi. If you take that, this exactly turns out like a rotation by an angle alpha about the y-axis, Exactly the same way you can show this. And finally, you might ask that what is the z-axis rotation in this rotation representation? So that basically, if you take a transformation, this is already something we know, delta 1 0 0 e to the power I delta 2. So this is actually, this is just basically saying that this mode A0 is just going through a glass plate with a phase shift delta 1, and similarly the mode A1 is just going through a glass plate with phase A delta 2. Nothing else. They're just passing through. This operation, when it operates on A1 and A2, this exactly turns out again. Let me just write this A2, A3. Acting on U of A0, A1 is exactly like a rotation about the delta 2 minus delta 1 about the z-axis. Sorry.
Can I make a comment?
Yeah.
Yeah. So this is very interesting that now you can see that if you think of instead of the A0, A1 basis, if you think of in this XYZ basis, it's it's exactly this action of the polymatrices. So it's like a spin Hamiltonian, XYZ Hamiltonian doing time evolution. And So means, but this is just a single spin. It's acting. It's doing time evolution on a
Yeah,
single
this.
spin, and the beam splitter is like the thing which is doing the time evolution
Hmm.
on the.
But except that it is made in a very specific way so that it gives a specific angle. You know,
It
like
is, yeah, it is made in a very specific way.
Exactly.
It is, but one. So now one can, maybe can imagine like having many beam splitters and
Yeah.
sending these things sequentially or parallelly and
Yeah.
some many body
Yeah.
computing. So
Exactly. So, but even for the simplest case, you see that what Diptarko is saying, now suddenly this beam splitter, which is a very something that you can imagine, you know, even my window, you know, has a partially silvered thing. So you see that it's in a XYZ. Basically, you're actually transforming the J's, right? So remember this J basically, you know, will actually have some, like in some state, you know. So suppose you start with a state which is aligned here, and you actually send it through a beam splitter and you ask the question, what are the operators there? You have basically made a rotation about the x-axis. You know, so you have actually made the state, you know, rotate. So we'll come to this, you know, like, and what happens to the rotation. If you didn't have a 50-50 beam splitter, you would have rotated by some other angle. You know, so you basically start rotating the state in the space, you know, and you can start visualizing them as just 3D rotation. So you see that if you want to just rotate the state about the z-axis, that's just by sticking pieces of glass. And similarly, we'll soon see that you know, this kind of processes where suppose I have a beam splitter here, you know, and light comes. A field is coming here, a field is coming there, and now you see that we are very powerful. It just doesn't need to be coherent states with amplitude and phases. They can be Fock state, they can be like many different states. They come here, a part gets reflected, a part gets transmitted, but I put a mirror here, you know, so that this goes there and then gets mixed. I put another beam splitter here, so how should I put it here? Like that, you know, and you see this light goes there, this goes here. This is a typical what we'll call an interferometer. Right? And ideally, you know, this is your optics. And ideally, you know, here we can place a glass plate, which will actually pick up a phase difference, you know, delta 1 along the wall. You see that this entire process of an interferometer can now be viewed as rotations. Like, so for example, you see that this process can be actually viewed as you start with an initial state, and the first beam splitter rotates about an axis about a certain amount. Then the phase difference actually rotates about the z-axis, and then again you go back along a rotation. So you see that finally this whole interferometer starts looking like comparison of two states. So you effectively, eventually, if whatever state you want to think of, either you can think in terms of operators, this rotation operators. Output is basically, you know, some transformation, some rotation times the input. Or you can say that there's an output, which is basically initially, you know, the first by a certain rotation about the x-axis, and then some rotation about z-axis, and again some other rotation about, you know, x-axis, and that's my starting from my input. These are like exactly two identical descriptions, you know, and we'll basically do few examples. Maybe we'll not do it in a formally in the class, but we'll do another tutorial where we'll actually use this to look at interferometers and what happens after beam splitters. Maybe I'll stop here and just take questions, because there's a lot more, and I'll come back to this again.
Sir, when I look at this analysis, it reminds me a lot of the Poincare sphere, and
It is, yeah.
And since you brought up the point of interferometry and using these operators, again, it reminds me of the parallel transport on the Poincare sphere, and then we look at the angle vectors.
You see that basically what we are doing, even like exactly Poincare sphere. So, so this is Poincare sphere, I think you will call when you're thinking in terms of optics. So you're thinking of these two states as like two polarizations, H and V, horizontal and vertical. So this is your Z axis. This is H and V, these two states, this is, again, you can write exactly the same way, 1, 0. So this exactly, so this is, you see, this is again basically a two-state system, and this you can map to the sphere, but the same, I think, if you're talking of a spin half, where the states are written very differently, but it's exactly the same. 1, 0, 0, 1, you would call a block sphere. And I think this is the general correspondence, that this is a SU2 group, and you can just write it in terms of a O3, like a rotation, basically. This is always true, I think, for any, this is just isomorphic, these two groups.
Yes, sir.
So
They have the same
you
number
have
of
a
generators.
representation.
Yeah.
And here you remember that, but it's very important to remember that the beam splitter kind of picks this up and actually takes, it actually basically, it's just like kind of makes it abstract, in the sense it says that it just two modes come in and two modes go out. What is the general transformation which will connect? And this whole transformation we can view as in a 3D rotation space, or in the spin space you will call the spin polarization state. Yeah. Yes, so that since you asked the question, I don't know if students are getting confused. Like, please ask more questions. These are very simple things we are talking of, but clarity is very important. So, for example, also remember that a general creation or annihilation operator, we are writing with this notations K and epsilon. Remember, K is the mode, the direction, and epsilon were the polarization vectors, So this formulation of a beam splitter is primarily, when I'm writing this Ks, they are actually, in this case, K1 and K2. So these arrows are basically two directions, And for example, here like the states, given this particular H or V, or the two directions K1 and K2 you're choosing, you can still have any state N coming in, right? So those states are not limited, because these are still a bosonic system. So you can have any N and M coming in, and you can ask what happens to this transformation. A state into state has N photon in 0 and M photon in 1. They are not limited to just 0 or 1, except this indices are limited by 0 and 1. And you can ask what happens to out. We'll do this kind of things, just to make sure that we understand. But you see that this actually will form a very basic elementary quantum gate through which you can actually build up a whole quantum computer with this kind of things.
Sir,
Yeah.
you mentioned that this RT matrix forms an element of the SU2 group. The S part of the SU2 group was not used anywhere. You never took that the determinant of the RT matrix is equal to 1.
So S is special. No, S is the
Yeah,
determinant.
it means that the determinant is equal to 1. So did we impose that condition anywhere?
Did we impose that determinant of 1? I think requires the inverse needs to exist, right? So that's basically a general condition which all these matrices need to satisfy, that they are normal, basically, right?
Yeah, so,
Is that right, Diptarko?
I think this mod R square plus mod T square equal to 1.
So that comes from the
Unitarity.
Yeah.
Unitarity, sir. Even the other
I think-
condition comes from the off-diagonal term of the unitarity.
Right. So
RT
Yeah, so
star plus
the
R.
determinant 1 basically is saying that this
RT minus.
the inverse exists, no?
Yeah, so as long as the determinant is non-zero, the inverse will exist.
Yeah.
And
So you get R square minus T square is equal to 1, and R dagger square minus T dagger square is equal to 1 from that.
yeah.
So determinant 1 is the same as the trace of 1.
Yeah, trace is for a two.
Yeah, it's a trace. is 1, I think. Yeah. And wait. So the special unitary group is set by these 3 operators. These are the generators of the group, which are the same as this thing, and then this Casimir operator, right? And basically the special part comes from the fact that the operators determinants, these operators are the ones whose determinants are 1, right?
Yeah, so the generators are sort of
So we are talking of the generators. We are not talking of that. I think there. But what Diptarko is saying, this is equivalent to the R square plus T square is 1. No?
Yeah. That's check.
In this particular case.
Yeah.
Yeah, normally if you release the special part, so then what is it just needs to be unitary, but basically the mod is 1, but not necessarily the determinant, right?
Right.
Yeah. So where is the special requirement?
So if you look at all of the matrices, like these one, for example, it trivially satisfies because cos square theta plus sin square theta is 1.
So here it's trivial, but you are asking a much more important question of the whole special unitary group too, right?
Yes, sir.
U2. Yeah. And I believe it's the same as the trace.
So the determinant of A is e power trace log A, sir. So if the determinant of A is 1, that means trace log A is 0.
Yeah. No, so not the trace as in not the trace of the operators. Yeah, so these are all traceless, right? But the generators, I'm talking of the trace as in like the unitarity, or like basically I think it would be the same condition as that it's trace preserving in the sense of the fact that the transformations are trace preserving. Yeah, we can get back to this. We can all think on this.
One way to see it is, of course, these are matrices which leave the identity matrix invariant, right? So identity matrix you gather equals to identity matrix.
That force.
Right?
That,
yeah. So if on the identity, and then you take determinant of both sides of this equation, then you get determinants square of u has to be 1. So that tells you determinant has to be either +1 or -1.
Yes, sir.
So from there, but then now you can ask why it leaves only but yeah, in order to get something not 1 higher, you have to basically, it can leave some other diagonal matrix invariant. That will also be unitary, say some number times identity matrix. But I think if we demand that it preserves the norm, I think it has to leave it can only leave the identity invariant.
Sir, actually, I think the -1, I mean the -1, because SU2 is not exactly isomorphic to SO3.
It's a double cover,
Yeah, double cover.
Yeah.
Reflections are excluded from SO3.
Exactly.
Yes.
So yeah, that minus is not there. That is true.
So that is why it's called diamorphic or something, no? Like some.
Yeah.
It's not really isomorphic. Yeah.
So double cover.
Yeah, but everyone can comment on how this is going in the sense that today I'll post right after I was waiting for this class. We couldn't do I think whatever we have done now, it should be fine. And then this kind of Saturday classes, we can really once you have the first tutorial, first assignment, we can discuss more during these things, and then we can have except that remember one thing, that once the assignment is there, you cannot just come and ask the assignment right away, but you can ask everything around the assignment, except that we really want finally for you to go and sit and work out. So once you look at it, I think it will become clearer. But please, this is what we are strongly expecting, that if you see all through the lectures, we keep asking like work out this, and so on. So you should already have an idea of how it's going for you, like whether we should be slower or whether the pace is fine, and you are actually getting time to work out things. But from the very beginning, if you go through the lectures and see as we are asking things to work out, if you do that, you should be comfortable. And of course, like you can ask more questions. Yeah, so I can save this.
Yes, maybe.
I should be able to save this, no? Where is the saving? Here?
Save. I think, yeah.
It's
No.
asking to print.
No, can you? I think it is automatically saved.
No, but then I need to have it as a name, no?
Yeah, so can you click on this bookshelf thing? Bookshelf.
Huh?
Bookshelf, that icon.
Oh,
Yeah.
I see.
So it is saved as some untitled page. So
I see. This one.
Yeah, so if
But
maybe
then I can figure out. Here I should be able to find it, and then I should be able to figure out.
Yeah.
Okay. Okay, so we can. Any other question? No, Deeptargo, so should we stop?
Yeah, we can stop.
Okay.
So right, and then next class will be regular class.
Tuesday, yeah.
Yeah, Tuesday. And then again Saturday we can again have a.
Yeah, next Saturday again. Okay.
Okay. Thanks.